slightly off my side, so I'm not sure. It's between the surface strand.
Okay, so I think we are going to first try to finish the Chapter-11. So once we finish Chapter-11, and we will get on, Chapter-10 first, and then we will get on Chapter-11. And then we will talk about the lab briefly. Alright, so Chapter-10 is about chemical bonding, the second chapter of chemical bonding. So in this chapter we studied, we continue with the first bonding theory called the Lewis bonding theory. So then we use Lewis bonding theory to do something like molecular geometries, and also like the polarities of the molecules. So like Tuesday we talk about, last week we talked about how to decide the molecule, the polar, non-polar. So recall what we did last week is like that. So the polarity of the molecule depends on two things. Depend on whether we have the polar bond, and also depend on the geometry of the molecule. So let's do this CRE as the starting point for this class. When you do that, let me just rewrite the two types of geometries. I call one type of geometry is the polar geometry. And all those polar geometry, you can see is modified. And there are 5 of that. So that's one band. And there's a trigonal perimeter. The T-shaped. Yeah, you can still working on the CRE. Alright, so I will squeeze here one more, which is square perimeter. Alright, so this is the 5 geometry, and we call them polar geometries. So the other group is the so-called non-polar geometries. Remember there are 5 basic geometries, 5 basic, one is the linear, trigonal planar, tetrahedral, find out whether your molecule is polar or non-polar depends on the geometry. We have 5 geometry, we call them polar, and then this 6th geometry called non-polar. Then depend on 2 things, depend on geometry, also depend on the polar bond. Right. So this CRE is about which molecule is most polar. That means all these 5 molecules are polar. So when you have those kind of questions, all of them are polar. So then depend on, because they have a similar geometry. So then depend on which molecule has the most polar bond. Most polar bond is the one with the largest delta EA. Right. So you know what is delta EA? Delta EA is the difference between the electronegativity. So all of them has the center. The center are the same. The center is tellurium. So then those atoms, fluorine has the highest EA. So the answer C is right. And also, like, if you have time, this week you should study the CRE. And you can, like, list these 5 different molecules in some order. In the order of increasing polarity or decreasing polarities. Right, so I will leave that for you to do the more practice. Right, so the next one is how many of the following molecules are polar? Alright, so depend on 2 variables. Depend on whether you have a polar bond, so depend on the bond polarities, depend on the geometry. If you are good with math, with those vector additions, and then also easy. You can always visualize each polar bond is a vector, is an arrow. And then you will see if all those arrows come out. But if you are not, if you don't like those approach, use this. Right. So think about these 5 molecules, and obviously to answer, those to get some idea about that those variables, you need to know what are the Lewis structure. Alright, so starting by draw the Lewis structure for the 4 molecules. Okay, I want to see the 4 Lewis structures. First one is very similar, xenon O2. So xenon is the center. So let me see the Lewis structure. Xenon is the center for the first one, and then you have the second one. The center will be the Si, the silicon. Okay, number 3, the libertarians. You have 2 carbon. For the 3, the structure is like this: carbon, carbon, and Br. And Br. So that will be the best structure. Then you finish the Lewis structure by saying how many bonds between what and what. And last one is trivial. So the Se is the only center.
Is it B? Or is it?
B, yeah, two of them are polar. So then you tell me which two are polar.
1 and 2.
1 and 2? Yeah, 1 and 2 seems right. Alright, so I give you a little time to draw the root structure. So the first one is xenon O2. So xenon is in the center, then you have O, even though I jumped one step, put a line there. But that's okay. So then you're counting the total number of electrons for this molecular. So you have 20 electrons. 20 electrons, so you distribute like this. So right now you have 16 on it, so you have 4 left over. 4 left over, you will put this 4 left over at 2 pairs. Right? So now you know this has 4 electron groupers. Right, so now what is the EG for this molecular? And what is our MG for the molecular? EG will be tetrahedral, and MG will be band. So those very simple problems. When the molecule is getting bigger and bigger, it's difficult to decide. So you will have more than one center. So what we talk about here is about one center. Right? So what we said here, and all the geometry has one center. So you first decide in that particular center whether that part is polar or non-polar, and then you add them together. So this is the band. Band geometry belongs to this, which means belongs to the polar geometry. So in those 5 geometries, any polar bond make your molecule polar. Any polar bond, no matter they are the same, they are different, or maybe some bond in the polar, some bond non-polar. So you see this bond here is between xenon and O, right? So this bond is polar. So then you have these 2 variables. And you have this geometry band, and then you decide any polar bond make the molecule polar. Okay, so therefore this one, so this one has molecular, and molecular. In this particular example, you have 2 chemical bonds, and it's polar. So it's a very interesting topic and also difficult. Okay? And even you just simply decide one center, the polar, non-polar, we have so many to consider. And obviously for some other moleculars, like supermolecular, like the molecule of DNA or a molecule of protein, then there's many centers, it becomes very tedious. But we starting from some simple, right? So that is the result of the first one. Because I already have this for this number 3, so I will continue with this number 3. And how many total electrons we have for this? And we have 2 times 4, which is 8. We have 2 times 7, which is 14. So altogether we have 22 electrons. And so no matter how much you have, try to finish the octet for the terminals. So therefore, I will put 3 more pairs for each BR. So that will give us 16 and 18. So what? Right. So that is 16 and the 8 and 8 is 16 and 18. So minus 18. So therefore, we have 4 more electrons left over. Well, you can consider either carbon as the center. So let's put both of them here. That means I finish this octet, and then we will see do another calculation, see how many left over. Then we don't have any left over. Right? So obviously, Now that is okay because we have all the atoms. This has octet, this has octet, that has octet. Except that carbon, what do you do? What do you do? Let's find out the best structure, right? So best structure will be you take like one of this, and you also take one of this. There's some other way, but those are not the best. So once I draw arrow like this, so then I will erase some of those. So I will erase this arrow. Just tell you what I did. So I will erase this arrow, and I will just draw a line here, draw a line here. Right. So that means we have a triple bond between carbon and carbon, and this is the measure. That is the best. Right. So then this geometry has two centers, right? And for this center, pretty much the same. Even though they have two centers, there's two same center. Right? So therefore, we'll follow the same line, and let's first identify for both of them what are our EG, what are our MG, what are our EG. Linear and linear for just for these two carbon, right? For these two carbon, that depends on how many electron groupers, right? The electron groupers, so we forget about that. Electron groupers, you can count in single bond as one group, double bond counting as one group, triple bond also counting as one group. Even though triple bond has 6 electrons in it, when you count in orbitals, you see that as 6. But when you count in group, it's just 1. Right, so for both carbon, there's 2 groupers of electrons. And then for both carbon, there's 0 lone pairs. So as we talked about before, if there's 0 lone pairs, so these two are the same, which means EG and MG are the same if you don't have any lone pairs. Okay, so therefore, tilde, so they're the same. And then what we said is those geometries for the molecular geometry. If I did not mention that before. So this geometry, 2 types is about molecular geometries. And this linear is here. It is so-called non-polar geometry. Okay? So once you have the Lewis structure, one thing for sure you know, we can see what is the geometry. Belong to this group or this group. Right? So then you decide what kind of bond we have. And I think the bond probably is, that for boron is 2.8. I mean for bromine is 2.8. For that. And this is 2.4. So what that means, if you use the cutting line delta En is about 0.4, and you will see the non-polar. But the bond, the polar and non-polar, not only depend on the delta En, and also those lines, those like this 0.4 is one number, and 1.9 is the other number. It's not really sharp. Right. So then, experimental result will show you the bond here. Let me see this bond between C and Br is polar. Now this type of geometry, this group of geometry is kind of very like a non-polar. That's why we call them non-polar geometry. So even though you have a polar bond in it, but not a guarantee you have the polar molecular. So clearly you all know in your mind, polar bond is a polar bond. It's only referring to very small part, in general, a very small part of your molecular. Most of the molecular have many of those bonds. So if you only have a polar bond, it's not enough to decide whether your molecule is polar or non-polar. That's why it's kind of tedious, depending on what you like. If you like to use vectors, try to add those vectors if they come out. If you don't like those, then I go that way, kind of confusing, use this, right? So this linear geometry, non-polar geometry, right? And so the result of this molecular is non-polar.
For the SiCl to Br2, you said that one was polar. Is that because of the difference in the delta En of Cl and Br?
Right. So this, first finish this one, let me finish this one first, right? So this one is non-polar because you can imagine this together in one center. Right? So in one center, you have two sides, left side, right side. Because otherwise, you will see, if you consider one side, this center, and that's polar, non-polar, so make it polar one side, and then this side, polar, non-polar, make it polar, and then two polar together will come out. Okay? But you can also consider these two together in one center, then that's what imagine this even better. There's one center, and then you have one center here, two sides here. Okay? And then we will say this type of molecular is non-polar geometry. Only possibility for those kind of geometry become polar is you have a different bond, a different polar bond. And for this example, if you consider this together in one center, this polar bond, both of them polar but the same polar bond. So same polar bond, not enough either. So that's kind of odd. Okay. And now go back to the question I was down in asking the number 2. I'm going to erase all those and then I will draw the number 2. Okay? And
Just want to take a picture of it?
yeah. So number 2 is, as I say, one center. So you have that SI center. Right? And what you do is just, right now you can put any one at any place. Just this is BR, and this is BR, this is CL, like that. Okay? And you're counting how many total number of electrons, right? So you have 4 times 7, because both CL and BR are in the same group, both of them have 7. You have 28, and then SI so give you 4, so altogether have 32 electrons. That pretty much you will have 4 orbitals. So you are complete orbital for all those terminal atoms. And so then minus 32 it becomes 0. Right? So now that finish these loose structures. That means silicon don't have any lone pairs. Right? So now you will see loose structure is the first step. And then you will see the number of electron groupers. Right? How many electron groups are on the central atom? You have more than one center, you do one by one. You have one center, that's easy, right? So then we talk about a different way to counting how many electron groupers. You can count how many single bond, adding all together, and plus how many double bond, adding all together, or simply counting how many atoms and how many lone pairs. And how many atoms on this Si? 4 atoms. How many lone pairs? 0. So altogether, so that equals 4. So 4 electron groupers, and that tells us the Eg and Mg. The Eg will be tetrahedral. And also you remember, if there is 0 lone pairs, then Eg and Mg are the same. So in this SiCl2Br2, and the loose structure told you there's 0 lone pairs, right? Right. So this geometry, molecular geometry is here, tetrahedral. There's only one center. That becomes simple. Okay. Now you have to examine what are the chemical bonds in the molecular. Okay. So we have 2 types. We have Si to Cl. We have Si to Br. If you use delta En, you will find out both of these two types are polar. Right? Both are polar. Now if they are the same polar, and you will cancel out, according to this what we said here. Okay? Now here they will not cancel out because they have a different polar bond. Alright, so that is about number 2. Right? Alright, so that's reason like this one is polar, and this one is polar. The first one, second one is polar. Right, and the last one is non-polar. Why the last one is non-polar? What is Mg? What will be our Mg for the last one? Octahedral. Right. Octahedral, then you read this. Octahedral, so you have Se in the center, and Cl, 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 so you have 6 Cl. Then you calculate the total number of electrons, 6 times 7, 42, plus 6, 48. And you just use one line first. So we call that glue. And then you finish the octet for the terminal. You do all the same for all the terminal if they need. If H is the terminal, and don't do it. Right. So you finish the octet for all the Cl, and then you counting how many you use. 6 times 8 is 48. So now you have 0 left over. So that's it. And then you examine the center atom. Do the center atom need octet? Does it have the octet? If it don't, use double bond. If it is, then you can optimize your structure by using double bond to make the former Chapter-10 smaller, but usually that will not influence your prediction of the polarity or the geometry. Alright, so 6 electron groupers on the Se. Right? And then that means you have an octahedral like this guy. For those geometry, once you know the geometry that belongs to one of those 6, for them to be polar, not only you have to have a polar bond, the polar bond must be different. If you have this one of these 6 geometry, and you have the polar bond, and all the bonds are the same polar, and all the bonds are polar, then you will cancel out. Now this example, you cancel out, that you have all the 6 are the same. Get it? Okay. Good. So that's non-polar. Yeah, so the last 2 non-polar. Polar and non-polar is very important. Okay? Well, we don't have too much chemistry yet, so we will talk about simply some of the physical properties. For example, polar will dissolve in polar, non-polar dissolve in non-polar. But if you see some of those polar bonds and you put into the molecule, then you will totally change the chemical reactivity for the molecule. Okay? For example, if you have those methane, okay, which is CH4, and now we know you will have a CH. Even though I draw it looks like a square, but you know it's a tetrahedral. So now you know that because there's an EN between carbon and H is pretty much similar, so you have non-polar bond. So this bond is non-polar. Now if you somehow use some of those techniques, use some of those chemical reactions, for example, light, that means light. And then you put a Cl gas. And then you will have something like this. So you can replace one H by a Cl. You can replace all the H by a Cl. It depends on how you control it. So once you have that, and then for this molecular, you kind of add a functional group. So now the Cl becomes very active because Cl bond to the carbon bond is polar. And you can do many chemical reactions. So therefore it's very important to recognize I think this, we're going to spend the time on the polarities, so study that, and it's very important. And then I'm going to talk about a little bit about the other boundary theories. So I just, the other boundary theory, one other boundary theory is the valence boundary theory. Okay? So in Lewis boundary theory, we think about the covalent bond. This is rather new, you don't have that. Is produced from a share of electrons. Okay. And now, at the time of Lewis boundary theory, is in like 1916 and 1990, we don't know the quantum theory yet. So people don't have those ideas like orbital, s orbital, p orbitals, but we know some of those electrons. So that's. So it's very, very classical. You don't have any idea about where are the electrons. You just see the electron, 4 electrons for like carbon, and 7 valence electron for Cl, or 4 valence electron carbon, and how they share it, and how many they share it. So now valence boundary theory is relatively new. So it's use like the quantum mechanical theory. Quantum mechanical theory that first come into is 1925. So 1925, that remember that Schrödinger equation is the key equation for the quantum mechanicals. So in 1925, Schrödinger introduced the equation. Now obviously the Lewis theory, they don't know like those equations yet. So then the valence boundary theory is pretty much how to use the Schrödinger equation, or in general the quantum mechanics, to solve the problem for the molecular. Now to solve the problem of even like a single atom of the Schrödinger equation is difficult. You can solve the equation for the H-like atom, as we talked about in Chapter 7. Which means you only have 1 electron. And there even you have some of those approximations. You have to separate like the time with the space. And then those space, X, Y, Z, kind of independent. Now if you have those complicated atoms, you basically cannot solve that with mathematical way. So use those numerical ways calculations. Now this valence boundary theory is pretty much, you just consider each atom, and each atom, and those 2 atoms come together, how can they become more stable compared when they are separate? So obviously to solve that 2 atoms is more difficult, because we know we cannot even solve 1 atom like helium. So what people do is they use like different those methods, those different like those numerical methods. One numerical method in solving those Schrödinger equation is the so-called perturbation theory. What is the perturbation theory is you start with those simple like 2 atoms, assuming you can solve that 2 atoms, and then when they come together, not only you have that 2 atoms, you also have the interaction between 2 atoms. Now you consider the interaction as some of those determinants. And these determinants, you can put them in different magnitudes. So the so-called first order, second order. So the first order, you are treating those larger determinants first, and then those sometimes those smaller determinants. Right? So anyhow, we don't have to worry about those details, how to get those calculations. Actually, once you started on those calculations, it become not too many people do those calculations, because you just buy some program and then just try some different try. And right. So then once you try that and you calculate, and you will see what is the best way to make those 2 atoms come together, have a lower energy. Because if you have a lower energy, that means they can produce molecule. Not all the atoms coming together can lower the energy, according to the experiment, according to the calculation. And obviously the calculation has to do with the experiment. So then what we find out is if you like want to produce a stable molecule in between, for example, 2 atoms, usually you will have those overlap between those orbital of the electron that is in, and more importantly, so the overlap should be that between two orbitals that both of them is only have one electron in it. Even though sometimes you might have one orbital that is totally occupied, as we study in Chapter 7, each orbital can only have 2 electrons. So in general, you have one orbital from one atom, another orbital from another atom, both of them only have one electron. And when they come together, they can possibly produce a chemical bond, become stable. And obviously you can have other possibilities. One orbital has 2 electrons, some orbital has 0. They put together also become stable. And so in this class, we only talk about one and one, and put together and become stable. So then you do those by calculation. You will see you tune those variables. You see, make this distance between 2 atoms, 2 nuclei change. You change, try different way, then you will see what's the result. So we try to get the lowest energy. So then there's geometry for your molecular geometry. So this atom here, what is the boundary line? That's the simplest one. If you have 3 atoms, this atom here, what is the other atom? Maybe on the other side. And once you get those lowest energy, then that's molecular geometry. So then you summarize like what we see the valence boundary theory is the valence electrons is reside in the atom, and in the atom they might in those standard atomic orbitals we know from Chapter 7 as p, d, f type, or when you do the calculation, so sometimes you want to make the 2 atom energy together become lower. So now when you do those calculations, you sometimes not only use those pure SPD, so you can tune it. You can say you first mix S and P in one atom, then leave the other atom just the P. Then how much you mix? You take one S with one P, you take one S with 2 P. You probably don't. There's a lot of details you can see like one S. Maybe not 1P, maybe half P. So all those different like tuning, you just make sure you have the lowest energy. But in this chapter, we will say we can do nothing at all. Either we will take 1P or take 2P. We will not think about those complicated situations, just like 1/3 P or 1/2 P. So that's what we think about. Okay. So first think about you are going to overlap those orbitals in the atoms and make them become stable. And what do you overlap? You might overlap S with S. You might overlap S with B. Or you might overlap those S with hybrid. So one example you overlap is overlap that S with P. For example, you will produce HCl. Another example you can overlap is so this purple one is sort of the sp2 hybrid dyes. So if you remember, we talked about last week in the lab. And then this red one is one with P from this argon atom. So then sometimes you can also like try to make your molecule stable, but also hybridize those terminal atoms. Usually we are not going to talk about that. I think this book sometimes, maybe the early version, have some of those examples. So those terminals also become hybridized. But you can see that two boundary theory compare side by side like this. So in the Lewis boundary theory, this is the same molecular sort of formaldehyde, and you only see the double bond between carbon O in the Lewis structure, then you share 4 electrons, and that's it. So in that double bond, they are stronger than single bond. Okay? So then later on you will see that double bond activity is stronger, but it's more active, chemically more active. So a lot of chemical reaction can happen on that. That kind of strange. You have a stronger bond, and that becomes like more active. But if you use this kind of theory, so even though you have 2 chemical bonds all together become stronger, But that two chemical bond not the same. One chemical bond called the sigma, like this. The other bond we call that pi, like that. And then the pi bond, even though it's adding together with the sigma, make that all together between this O and the carbon becomes stable, but that pi bond by itself has more electron and not that stable. A lot of chemical reaction happening. Especially for some of those reagents, they're seeking for electrons because this kind of electron abundance. Alright, so now let's go back to the valence bonding theory. So we know those electrons in those orbitals. You can take those s orbital overlap with the p orbital, or take the s overlap with s, okay? Or you take those p, those are the atomic orbitals, overlap with those guys. We call it hybrid. So then you will see this chapter's opening statement by some of those philosophers. They said like no theory can predict everything. The similar thing for valence bonding theory. So valence bonding theory is good with some aspect, but it fails with some. So what you do, you just do the calculation for most of the molecules. If you find results, and most of them you have the similar result. So now, as we know, the valence bonding theory use either the atomic orbital to the overlap, or use hybrid orbitals. Atomic orbital you already studied in Chapter 7, SPDF. So you don't have to worry about that too much. Now you will see how can you make your molecule become stable by first, for some of the molecules, you will take those S, P, and D in one atom, on one atom, mix them first, and then you do the overlap. So the reason we are going to use those hybridized orbital because they minimize energy by maximize the overlap. So the particular type of hybridization that occurs, or how much that occurs, you can take one S with one P, you can take one S with one half P. We are thinking about just, as I said, just very clear. So one S, one P, one S, 2P, one S, 3P, one S, 3P, 1D, one S, 3P, 2D. So we will make them very sharp. But in reality, you don't have to be that sharp. Right? And so, because you don't have time to really do the calculations, so what you do, in this class, we'll just use the number of electron groupers on the central atom, even though that can also happen for the terminal atom, to decide what kind of hybridization to use. And that becomes very simple. So that gives us some idea. It works pretty good even though you use simple. And for example, if you study organic chemistry, it's very important to know those carbon is very, very good with those hybridizations. So what hybridization is for carbon, that will change the carbon's geometry, change the carbon's reactivity, and change like the carbon's basicity, acidities, and so on. And that's kind of dramatic. You'll see that when you study more and more chemistry. And to show you those hybridization kind of very naive way, why it's important to have the hybridization, let's consider like beryllium, Be. Okay? Now the Be, the electron structure, in the Lewis theory, you don't have to worry about Lewis, the electron structure, because Lewis don't know the electron structure. He don't know like what is. I mean, when he have the theory, later on obviously, everyone knows the theories. So like according to the quantum mechanics, so the beryllium Be has 4 electrons, number 4, right? And you have 2 electrons in one S, 2 electrons in 2S, so all the electrons pair up. And then according to the calculation of valence bonding theory, it's not good with overlapping. Best overlapping is have an electron in one orbital. Okay? That's also possible. You can take a beryllium with some of those transition metal. Transition metal has a lot of those empty orbitals, like d orbitals, and so you can use these two electrons donating all together to like those d orbitals, and then they can produce coordination compound. But in general, what you do to explain those results, so what you think about is you first use a little bit of energy to like promote or to excite the electron from the 2s into the 2p. So even though that will take use some energy, but that will like later on that will like release it. So then what you do, you can take these two orbitals, by themselves to the overlap, like in sulfur. But for beryllium, so experimentally we find out, also from calculation, the best way for beryllium to produce chemical bond is first mix this 2s orbital with the 2p orbital and produce so-called hybrid orbital. And then use that to the overlap. And if you take one of those s orbital, you take one of those p orbital, even though you have a 3p orbital, but for beryllium you don't use the other two, you only use one of those. You start with two of those atomic orbital, you get two hybridized. Now that's mathematical way. So you have hybridized, and that you can see the structure. This one looks bigger, and that one looks bigger. But bigger with small one together is one orbital, one hybridized. But then, those mathematicians, they say, okay, so we will maximize overlap. So what you do, you will take this side to the overlap. And that obviously is bigger than that. So therefore, you put them together, it looks like so you have this is two of those sp hybridized orbital, looks like that's one of those p orbital, but this here, you have two of that. We put them in this geometry because that is from calculation. If you have these two geometry like this, and then if you have this beryllium in the center, the beryllium nucleus here in the center, then you put like somewhere here, maybe a fluorine atom, that will give us the lowest energy. And this is the same for most of those molecular has two electron groupers. And no matter that two electron grouper, like in this example, two single bond, or maybe in the next example, a triple bond and a single bond. As long as you have two electron groupers, so then for most of the molecules, the best way to lower the energy or do the hybridization or do the overlap is use the sp hybridizations. So therefore, for our study, it's very simple to decide what kind of hybridization the central atom use. It's kind of boiled down to what we did here. You just draw the root structure, decide on the central atom how many electron groupers, no matter they are from those atoms or from the lone pairs. As long as you have two electron groupers, and then your central atom are going to use sp hybridizations, which means you take one of those s orbital and one of those p orbitals. Right? And so this, because we did not care about whether this is from bond or from lone pairs, just see the two groupers. So therefore, you have to also examine what is the molecular geometry. So if you have two electron grouper, your electron geometry will be linear. But in this class also simple, so we don't consider any lone pair on the central atom. So therefore, two electron groupers, that means your electron geometry is linear, molecular geometry is also linear. But for some other possibilities, if you have, let's say, three electron groupers on the central atom, and like that, and then, if you have three electron groupers, Now we are going to use what do we get the conclusion. We don't have to worry about how we did the calculation. We just see how many electron groupers on the center atom. So if you have 3 electron groupers, we know the electron geometry is trigonoplanar, and the molecular geometry, because we just counted 3 groupers, we did not see 3 lone pairs. We cannot be 3 lone pairs. We did not see like 3 atom, 1 lone pair, 2 atom, 1 lone pair, all the 3 atoms. So therefore, you possibly have different molecular geometries, right? So your molecular geometry may be trigonoplanar and maybe band. So ideal angle is 120, but that depends on the molecular. You can like tune it just when you do the calculations. And then this kind of geometry, the molecular geometry, which means flat. So if you have 4 atoms, all the 4 atoms is flat. The center is on the table, all other 3 is also on the table. If you have the band, you have 3 atoms. That means the 3 atoms obviously cannot be 3-dimensional. Now you see the one example of this kind of molecular is this guy, and this is like the one example of those organic acid, or formic acid. Okay? You have carbon here, you have oxygen here. Okay? So if we examine this carbon, and on this carbon there's 3 atoms bonding to it. Okay? So then one way to counting the electron groupers, is just counting how many atoms bonding to the center atom, okay, and how many lone pairs. There is 3 atoms plus 0 lone pairs. So altogether, this carbon has 3 electron groupers. And according to this chapter, we can simplify our discussion. So whenever we have 2, use SP. Okay? Whenever we have 3 electron groupers, no matter 3 atoms or 2 atoms, 1 lone pair, you will see this center atom or this interior atom use S, which means 1s, but there's index here and 1. Okay? This 2 does not tell you have 2 electrons. The 2 here tell you use 2 of those p orbitals. So 1 s orbital plus 2 of those p orbitals, altogether you will produce 3 of those hybridized orbitals. Right? So then you wonder, you have 3 orbitals, 3 hybridized orbitals from this sp2, but on this carbon, altogether you have 4 chemical bonds. Where does the 4th chemical bond come from? You can reason in the 3 chemical bonds come from the overlap of that 3sp hybridized with something else. But here you have 4 chemical bonds, so where does the 4th overlap come from? And where the 4th bond come from on that carbon indicated by the arrow? When you see magic. The oxygen, the double bond between this oxygen and carbon is double. Okay? So what you use, here is this double bond, one of them is the overlap between this carbon and that oxygen. Okay? So when you do the overlap, you have to think about what they use. They use s orbital, p orbital, or the hybridized sp or sp2. Okay? So we know this carbon hybridized sp2. Okay? So this bond, this bond here. Okay? So let's say either one. If I come to this, okay? So this overlap between sp2 with the p on the O. Okay? Now where the other come from? The other come from, you have to think about what the level over. There's a valence amount here is about overlap. Whatever level over you possibly can overlap. What's the level over on carbon? You don't use it. By P, right? When you see P2, that means you use 2 of the p orbitals. There's 1 p left over. Okay? The unhybridized p orbital left over. So what the carbon do is use that orbital overlap with another p on the oxygen. So here will be the p. We can write something like this. So this carbon use a p, and this means chemical bond. Overlap with oxygens p. And so this we call the pi type. And this we call them sigma type. Right. So we will talk about in more details about those sigma and pi. So just sometimes you wonder because those numbers were not matching how many bonds on the center atom. So you have 3 of these, but on this center atom we have 4 chemical bonds. So 3 chemical bonds come from the overlap of this sp2 type with something else. One example is with p. And then the fourth one is the overlap between the leftover p with something else. So what it looks like, how you do the hybridizations, so then you know from the name, very similar as the name for sp. When you see sp2, right, so we have 1 of those s orbitals. Now this s orbital, as we studied in chapter 7, maybe 2s, maybe 3s, depending on your atom. And then those are the p orbitals. And obviously you cannot have 1p. Maybe 2p, for example, when you think about the carbon. Maybe 3p if you think about phosphorus or silicons. Right? But for every p, no matter you have a 2p type or 3p type, altogether you have 3 of that. You might not use all the 3. You might use only 2. You might only use 1. If you use 2, and then you plus that one, altogether you have 3, so therefore when you mix together you have 3 of these. But the usual way to put these 3 together is you are not going to see this little one. So the little one is like overlapped by the larger one. So even though here we only show like these 3, but actually you will see there's also a small part. This small part is not overlap. You can see it here, but that's not important. Alright, so you continue. You draw the Lewis factor, you will see some of those central atom has 4 electron groupers. Okay? So when they have 4 electron groupers, so then you know the electron geometry will be tetrahedral. Right? So then what is the molecular geometry depends on how many atoms, how many lone pairs. Now the question is the bond angle you have to also worry about. Bond angle, are they perfect 109 or are they different? Those are little details. So then what we see in this section is what kind of hybridization the central atom used to make that, to accommodate that 4 electron groupers at least. At least that 80 electrons. So there's adding one more because you need 4 like orbitals to accommodate that 4 electron groupers. Even though some of the electron grouper has like 4 electrons, so therefore you have to think about some other chemical bond. Okay, one example is this methyl amine. So you have this part methyl, that's amine. And you draw the Lewis factor, so this is finished. So this carbon has 4 atoms bonding to it, so therefore 4 electron groupers. This nitrogen has 3 atoms bonding to it, and 1 lone pairs, that's also 4 electron groupers. So therefore both of these carbon here, this nitrogen here, the best way for them to do the valence bonds or do the overlap is use those hybridization orbital before they overlap. So therefore they use sp3 and sp3. And then the bond angle pretty much for most of the atoms just like those. So here is not really perfect tetrahedra, neither that one. And then the angle between this one and this one will be 109, something like that. Probably because that lone pair here, that means that becomes smaller. That can change. Okay? So here is one carbon. Okay? Now here, if this part is not one carbon, it's like a bending ring. Blah, 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 I see this carbon here, but it's a circle. Now that bond angle becomes totally different. Okay? So what do we say here? Just on a small scale. So sp3 hybridization is very similar as sp2. What you do is you take those s orbitals, mix with all the 3 of the p orbitals. Alright, so then you can go on with more hybridizations. Okay? Because some of those molecular group structure, the center atom, have 5 electron groupers. So here is one example. You see this molecule, and this I in the center. And you have like 3 oxygen, 2 fluorine. You draw the group structure, you have this very complicated problem. But at least you know you have 5 atoms bonding to it, and no long pairs on the center atom. You have 5 groupers of electrons. Okay? So now what is the best way to do the overlap for the chemical bond? Well, you just use the number. Okay? If you have 5 groupers, that means those numbers adding together is 5. Okay, then, so this is 1, this is 1. So 1 plus 3 plus 1 is 5. And then 5, matching your number of electron groupers. It's so simple for our for most of the molecules. And your electron geometry work with the sort of trigonal bipyramidal. Right? But that depends on how many atoms bonding to it, how many long pairs bonding to it. And you can have the trigonal bipyramidal molecular geometry. You can have that T-shaped geometry. You can have the seesaw. You can even have the linear.
So basically, we just have to memorize everything.
Basically, yeah, you just like root structure, and then you know how to draw the root structure all the time. And then you sometimes you can even like optimize the root structure by putting double bond, triple bond, use a formal charge. Formal charge is a different way counting the electrons. And then you are counting the electron groupers, so that's another different way of counting electrons. Yeah, you pretty much just you can memorize that mechanically, or use some of those tricky way memorize, or you can just use make sense way. And you think about it, you need you have 5 electron groupers, so therefore you need at least those 5 orbitals to accommodate. And so then how you get a 5 orbital to accommodate? You can take all the 5D, but that will not matching your geometry. Any other questions? All right. So that is how the entry diagram looks like if you use the sp3d1 hybridizations. So s orbital low energy, and p orbital bigger high energy, and d orbital even higher. We want to see this because we want to understanding, or we want to know what kind of atomic orbital we're going to use to do the hybridizations. So usually you will take those atomic orbitals that is very close, okay, or have a similar energy. If they are too far away, so you don't take a 3s with a 5p. Their energy is so much different. If the energy is so much different, and those is kind of wave function, so their frequency different, their node is different. When you put them together, so they don't have a good overlap. You will come out a lot of those. Alright, so then the next, that's one more example. And you probably also want to, you have time, like pay attention to those kind of notations. Okay? So I briefly tell you before, so this bond here, right? We call it a sigma. So this Greek letter sigma. And then you will see this kind of notations. This AS means arsenic. And then in the parentheses, that means what this arsenic used for the overlapping. And that tell you is sp3d hybridized orbitals. And this means chemical bond. Overlap with fluorine. So that what orbital the Freudian use? The Freudian use not as P hybridized, it simply use P. And then you also use what kind of P? Use 2P or 3P, depending on the electron configuration of a Freudian. Yes. I'll review what we studied in Chapter 7. Right?
By the period?
Yeah, by the period. So you will see the Freudian will have 1s2 and 2s2 and then 2p5. So that means one of those electrons that is not a pair is in the 2p. And that's what just you think about that Freudian just take that 2p orbital without any modification, without any change. Just use that directly and to overlap with arsenic. Got that? Right. Now, continue with even larger number of electron groupers on the central atom. In this one, you have this. We have two different examples here. Obviously, we have that example with the BrF5, and here is sulfur F6. But both of them has 6 electron groupers on the central atom. Understand? Okay. So therefore, this Br use this type of hybridizations. And then this sulfur, they also use Sv3d2. Right? So then, continue with this kind of notations. You will see this bond, is a bond here, between fluorine and sulfur. And this is like one advantage, one more step of the valence bonding theory. It will tell you the bond is produced between what atom and also use what kind of orbital or orbitals. Okay? So that tells you this sulfur use a hybridized orbital. The hybridized type is sp3d2. Okay? And then overlap with the P from the fluorine. So whenever you only have like one bond between two atoms, and you will call those kind of bond sigma. Okay? So sigma. And that means the overlap is better than pi. The kind of head-on or add-on. And so then for this type of hybridizations, what is your molecular geometry depends on how many lone pairs. Okay? If you have one lone pair, you have a so-called square pyramid. If you have two lone pairs, you will take that away, your molecular geometry becomes square planar. Right? But even here we have two different molecular geometries. So both of these two molecules have 6 electron groupers on the central atom. So both of them use sp3d2. So electron geometry for both of them is octahedral. But the molecular geometry for this one is a square perimeter. The molecular geometry for this one is octahedral. So that's continue what we studied in the previous session. So this session, what is new is use the number of electron groupers, decide what you use. Do you use SP? Do you use SP3, SP2? Right, now this table summarizes how you predicting the hybridizations. The book emphasizes use those electron geometries. I think electron geometry pretty much come from the electron groupers, even though sometimes these two not exactly matching. So therefore, for our purpose, so the matching is good enough. You just take the number of electron groupers instead of the geometry, so because these two are pretty much equivalent. So you have 2, use SP. So again, that this number, so you have S1 and P1. Let me rewrite S1 and P1. So therefore you have 1 plus 1 equal to 2. Now these 2 are matching that 2. So S1 and P2, we have 1 plus 2 equals 3. And these 3 will measure as 3. Got it? Right. Now let's see, you can identify what we just studied. Okay. So I give you one of those amino acids, glycine. Amino acids are those kind of compound. Has this acid part, and this is the acid group. Okay. Now this carbon is called alpha carbon. Okay. So this is our acid group. This carbon, the right bonding to that acid group is alpha carbon. Now we talk about those amino acids like in the protein in our bodies. Okay. So about those alpha amino acids, which means on this alpha carbon you have this part. This group is the amino group. Right. So just give some idea about that. Those kind of molecules is very important if you study biochemistry or organic chemistry too, the last 2 chapters. So now if I keep this structure with all those atoms, with those lone pairs, okay, let's identify this N. Okay, use what kind of hybridizations? This N is what hybridization?
SP3?
SP3. Now how do you know it's SP3? It's tetrahedral electron geometry. Or you count in the electron groupers. How many electron groupers are grouper on this N? 4 come from 3 atoms plus lone pair. Okay. So 4 you will be SP3. Okay, now this carbon is using what? What does this carbon use? This carbon use here.
4.
4, that means you 4 bond, which means 4 atoms.
SP3.
SP3. Okay, now what does this carbon use? SP2. Now red, why is SP2? Trigonal planar. There are also 3 electron groupers.
Wait, are we going to be learning about sigma bonds and all that stuff?
Yeah, so we'll see. So then, whenever you have a double bond, one is sigma, one is pi. Whenever you have a triple bond, one is sigma, 2 is pi. Right, now what kind of hybridization does O use? SP3. Why SP3? Yeah, you can see band. Like band come from what band? So I think the electron group have more connections. Alright, so then let's see if you understand when we see those hybridization. So what do you use? How much do you use? What do you say? What kind of hybridization we talk about? SP2. SP2. And how many SP2 you can have? Once you mix them, how many of those you can have? How many SP2 you can have? For the question, we don't talk about that before. Well, when you mix SP3, how many you have? When you mix SP, how many you have? How many hybridized SP you have? How many hybridized SP2 you have? How many? 3. So 3. So that 3 will come from, you have to use those number ending together to get 3. So how many of those S type and how many of those P type?
S is 1.
And S, there's only one S. Okay? And then that means you're going to take how many P? 2 P. Those are, we call them here, call them index, not the electron number. So therefore the answer is E. Have that? Now if I think about SP3 and D2, okay? So let's see how many S and how many P and how many D use. If I have this kind of hybridization orbital, how many S it use? One. How many D it use? Three. How many D it use? So adding together you get 6, which means you have a 6 of SP3 and D2.
So we were just overthinking it, it's E.
Alright, so then how do you decide what kind of hybridization you use? I mean, there were like, you have the sigma, the fundamental, you have to draw the Lewis factor, okay? Draw the Lewis factor, you can either use the electron geometry or the number of electron groupers. D. 2, which 2? Let me see, the middle 2. Try to do a very quick practice and see if you can have time. Yeah, I think not the middle 2. Not the middle 2. So there are 2 of them use SP3D. The second one, you can do a very quick calculation. You will see you have a 6, 7, give you 42 electrons, right? But you have 5 terminal atoms, so each terminal atom will take 8. So you use 40, you have 2 left over on the center. So therefore you have a lone pair on the center. And so lone pair plus 5 atoms, so you have 6 groupers. 6 grouper on the center atom, that means it use SP3D2. Which 2?
What?
Very good. So the last 2 use SP3D. What did the first one use? What did the first one use?
SP3.
Very good, SP3. What did the second one use? Yeah, SP3D2. Right. So we have time, and if you have some question, draw the Lewis factor first. So this if you can recognize this picture. What is the hybridizations for the xenon, which is center? Usually we only consider about the center.
Is it E?
Is E? Yeah, so you can see there's 6 groupers of electrons. Okay? So you have 4 atoms, right? 4 40 atoms plus 2 lone pairs. Right. Okay, so according to our name, all the sigma bonds are the sigma bond. So then you just recognize for this question and what overlap you use. It's end up with you have to recognize what kind of hybridization the center atom use. And you also have to recognize or remember what is the electron configuration for the terminal atom. What is the electron configuration for the terminal atom? That is the Chapter-7. What kind of hybridization this use?
Is it E?
Is
A.
very good, very good, very good answer. Why is it A? the real difference between A and E, right? I think that's a very, you probably did not pay attention to here. So here I see it's 3p of f, and here's 2p of f. You did pretty good, or you did pretty good to identify the sulfur used sp3d. Right? So why the sulfur used sp3d? Use sp3d, that tells you how many groupers of electron it has. If you think about the sulfur use sp3d hybridization, right, how many groupers of electron on the sulfur? 5. Okay? Now this is one of those molecular geometry that come from 5 electron groupers, those kind of geometries. Right? So that this means this structure missed a pair of non-bonding electron here. Right? Right. So this is our lone pair. Now one lone pair plus 4 atoms altogether have 5. Right. Now the difference between A and E is your what do you call it? Recognize or just sounds very kind of you see this fluorine, right? Fluorine is 1s2, 2s2, and 2p5. Okay? So therefore, you want to use the 2p. Okay? So here, you have one bond here, right? What do you call this bond? Sigma or pi? You call this sigma or pi. What are you write on the top?
Sigma.
So this is sigma. Okay? So then you write semicolon. Okay? Now this bond is between what and what? Sulfur and fluorine. So what you write, your sulfur and parentheses. Okay. In the parentheses, you want to tell me what kind of orbital is used to the overlap. You already know that. S use what? sp3 and D. Okay. And those notation depend on your organic chemistry class. So one time I emphasize that, but most of the time you don't get it. So probably, but those are important. Okay? So now they're bonding to what? Sulfur bonding to what? Fluorine, right? So can you see fluorine use what kind of orbital? P, so pretty safe P. Okay? So those are notations, okay? It's kind of very important to me, but sometimes those people just emphasize, you just learn something, you don't have to worry about too many of those reasons. So what is the hybridization of the sun atom in the xenon F2? Mike, it says D. Why is D? Why is D?
5.
5 electron groupers on the center atom xenon. Yeah, so that's. Alright, now let's talk about in more detail. So the sigma and sigma bond and pi bond. Right? Now the difference between sigma and pi bond is coming from the way they overlap. Now what bonding theory emphasizes the overlap? We have 3 bonding theory. The Lewis bonding theory, the valence bonding theory, and molecular bonding theory. Lewis bonding theory emphasizes the share of electrons. It doesn't tell you like overlap, those kind of concepts. Okay? So the overlap comes from the valence bonding theory. So valence bonding theory about the overlap, and the overlap is the overlap between those orbitals, whether the orbital is S-type, P-type, or sp hybridized type, or sp3 hybridized type. Okay. So then you will see the overlap, either those kind of overlap way, which is so-called head to head. So whenever you have head to head, or some people call it end to end, you only have one overlap region. That one overlap region is cylindrically symmetrical around the internuclear axis. This is very, very important. So if I draw the internuclear axis, so this is my internuclear axis. Now this part is overlap. If you cut a cross section of this overlap, you will see it's perfectly circular. Okay? So this will be the cross. So this will be the cross section. And then your line, that red line will be the dot in the middle. Get that? Right? Now if you cutting line here, and you will see you have one part, maybe not that perfectly circular, but that's the shape of the p orbital. Another part here, let me change that a little bit. So both of them like that. Now what is your internuclear axis? It's the dot in the middle. Understand? Now for the sigma bond, see the dot right in the middle of the electron cloud. Now for the pi bond, your dot or your internuclear axis is in the middle. And then on that dot, you pretty much have no electron density. It's kind of a node. So zero possibility of the electron on the dot. Right? And this is very important for this boundary theory, because that tells you if you have like those a sigma plus a pi in between two atoms, and then that will make your two atoms cannot freely relatively rotate. If you rotate, that will break apart these two overlap regions. And that is a very important concept in chemistry. If you have this bond here, and in this bond here, that is between this carbon, and this bond is only a single, and therefore is a sigma. And sigma can relatively freely rotate, even though when you study those molecules, I'll tell you, you also have those kind of equilibrium structures called Gaussian structures. It's kind of not perfectly freely rotated, but the room temperature, the thermal energy is enough to make it freely rotate. But if you have a molecule like this, so from a Lewis structure, we know there is a double bond between carbon and carbon. Now this valence bond theory gives us more details. So that double bond comes from what? Then you know one of that bond is sigma. And that bond is okay, can freely rotate. Okay? But these two bonds together connecting this carbon with this carbon. So therefore this bond here is also between this carbon and this carbon. That bond cannot freely rotate. The result is you have more possibility to connecting those kind of atoms. For this example, Cl and Cl, both of them actually below this double bond, or on the same side of the double bond. You call those kind of structure and we call it Cs. Or you can, so this is our sheath structure. And this is our trans structure, which means you have the CL on one side of the double bond. You recognize that? And then this CL is on the other side of the double bond. This double bond you can imagine up side, bottom side. Alright, and this will be two different molecules. You cannot change them from one to the other one at room temperature, because the room temperature, if you don't use some other chemical reactant, it cannot break this pair bond. Okay, so now what we can summarize about those bond type is how they overlap, and what kind of chemical bond is what. So overlap, as you know, for the sigma is head-to-head, and it can relatively freely rotate. For the pair bond, it's side-to-side. That cannot freely rotate. Now you also know, for every single, no matter single between H and H, between H and C, between whatever, if you identify that only one dash is a single, and those one dash means sigma. Why that? Because that is natural. Naturally, you want to have a low energy. The best way to have a low energy is to maximize the overlap. And the overlap, head-to-head, is better than side-to-side. But when you have multiple bonds, you already have one head-to-head. The other one cannot head-to-head because of geometry limitation. Right? So whenever you have a double bond, one sigma, one pi. Whenever you have a triple bond, there's only one sigma, or you can memorize that. There's always one sigma, or only one sigma between two atoms. No matter how many bonds are there, if you have one, there's one sigma. If you have two, there's one sigma, or the other is pi. But as I said, there's only one way to make that head-to-head. You want to make more bond? The other bond will be not head-to-head, will be side-to-side. Alright, so again, this molecular is about that formaldehyde. So you have that C double bond to O, and then you have single bond to H, single bond to H. You know the Lewis structure, that will tell you like this. So then you add like two lone pair here, so that make everyone overhead. Okay? But the valence bond theory will tell you in more details. Okay? So you will know like the bond between this carbon, this H, okay, is sp2 on this carbon, overlap with one S on this H. And between this carbon and this O, there are two bonds, the double bond. One of them is sigma, that come from the overlap of this carbon, right? So this carbon use sp2, and this is one of them. sp2 here, and sp2 there. So you have three of that. Right. So now what this bond here, this overlap between carbon and O, there are two bonds. One bond is between this sp2 and one of this orbital from the oxygen. Okay. Well, so that's why I said for most of the atom, we don't have to worry about those hybridizations for the terminal atom. And well, it looks like this picture shows you. What do you think? What it looks like? This O use what? Does this O use simply use those p orbital or use hybridized orbitals? Hybridized. What kind of hybridization does O use? So then, so this is also SP2. This SP2 is from O. Alright, so then both of them use SP2. So then this is our pi bond. That comes from overlap between what and what. So the C use what orbital, and O use what orbital. So if you can identify that. If you know that, I will feel very happy for today's class. So that bond here, okay, there are two parts on the top and the bottom. That's the typical characteristic of the pi bond. You have two parts, maybe on the top and the bottom, maybe in the front or in the back. The two parts that come from the overlap of what kind of orbital. Why not certain? You have,
I
you
don't know
see,
what you're
you see the notation here, SP2, right? So SP2, that means how many P you already use in produce these three. How many P you have already used to make this 1, 2, 3 here? You use 2 of that. Right? So one level over, that level over, okay? Yeah, so that's the theory. you use that by level over, and then level over from this carbon overlap with the level over from this O, that'll make that pi.
Oh, because there's two electric groups?
They call it the SP2 hybridization. Very good. So I feel kind of happy. No, very certified. Alright, now this one can be really good. Can now tell me what kind of this is for what molecule? This is for the molecule called acetylene. Okay? And this is for this. The Lewis structure is carbon, triple bond carbon, and a single bond H, like this. Now this bond is a triple bond. That means we have 3 bonds there. Okay? Now let's identify one by one. So this bond you call what? What do you call that bond? Sigma or pi? Sigma. Right? Okay, now let's identify that sigma is come from the overlap of carbon with carbon. Okay, forget about that. That kind of error right there. Carbon, parentheses, overlap with carbon, parentheses. So you can parentheses tell me what kind of orbital you use for the overlap. As what? SP. So this is SP, and this is also SP. Right? Very good. Very good. So now let's talk about this. This is pi. I call this pi 1 and pi 1. But each pi has 2 parts, right? So pi 1 on the top and pi 1 on the bottom. And this pi 1 and pi 1 come from what overlap? Carbon is what? With carbon is what? Now carbon is P, right? This carbon is P. Very good. So now let's call this part, if you can visualize, this is in the front. We call that pi 2. And then that part, see that little part there? And then we call that pi 2. That will come from the overlap of carbons of what with carbons of what? Huh? And also carbons of what with what? Right? P and P. P and P. Okay, very good. Then what else bond we have in this molecular? Is the bond between this and this. These are the same. Now tell me the bond between the H and the C. The H use what? The C use what? Fill in the blank. What does the H use? S? What S? What S for H? 2 S or 1 S? 1 S. Very good. Because that's, you only have 1 electron. Very good. And so this, by the way, this bond is what type? Is sigma or pi? Sigma. Any single bond is sigma. So this is sigma. Right here. So this is sigma. Right. And let's finish. What kind of orbital does C use? S what? SP. Yeah, that's so this is SP. How many SP on one center? If you think about the SP, how many SP? How many SP? How many SP? 2. Adding the index. There's 1 S, 1 P. So there's 2. And 1 you use, so 1 you use, so this is 1 SP. So 1 you use to bonding with carbon. So the other one you use to bonding to the H. So you have 2 SP. Very strange. How many SP3 and D? How many SP3D? Now this time you get it. How many SP3D are there? 5. Okay? Why only 5? So when there are 5 index. Okay? So these are called the index. Okay, I think this is not because of difficulty, it's because of the information is overwhelming. And you have that's why you study before the class. Right, so how many pi electrons? So just be careful, we talk about electrons and bond. So even though you have a single bond, pi bond, then you know for every 1 pi there is 2 electrons. Right? For every 1 sigma there is 2 electrons. If I give you this structure again, this is called another amino acid, an aspartic acid. So here you have 2 acid groups. This is acid group. This is acid group. The alpha carbon is this alpha carbon, this alpha carbon. Okay? On this alpha carbon you have amino. Okay? So therefore this is our amino acid, and this is our side chain. All those 20 amino acids, they all have this part similar. This part depend. Okay? You can have simply cutting all those off and H. You cut this off and this become CH3, so you have different, all those different structures. Right? This is B. That means we have 2 pi bond. Right? Very good. 1 pi from here and another pi from here. Whenever you have a double bond, right? So that is 1 pi. Now let's continue with this problem, right? So I ask you how many sigma and how many pi? D? E. Very good. Why how you get there's a 3 pi bond?
Because the triple bond has 2 pi bonds and the double bond has 1.
Yep, exactly. So this is the triple bond has 2 pi bond. Okay? And this is our double bond has 1 pi bond. All right. So that's about how you know how many sigma, how many pi. And now we talk about a little bit about molecular bonding theory. molecular orbital bonding theory. Molecular orbital bonding theory is another specific application of one method of solving that quantum mechanics equation is a sort of use variational method. And you cannot solve the equation exactly, but you can use different way. So in this way, it's kind of you first make some of those educated guess. So you think about you want to finding that orbital that were all over the molecular. So what does it look like? And one very trivial guess is probably each atom will contributing some part to the orbital. And you know those atoms before get into the molecule, so each of them have those sp and those different types. So then what you use is think about they will use those valence atomic orbitals. So even though you probably also think about those inside orbitals, but so this theory also depend on the other theory. So you don't have to pay too much attention to those electrons that is inside. So the one trivial way is just use a sort of the LCAO, linear combination of atomic orbitals, and so then you just again kind of very very interesting work. You just change the percentage of each orbitals, sort of the weighted, until you put them into the program and get a better energy, get a low energy. So then the result is for the second row, for the second period element, and we have this few molecular orbitals. Okay? So you read this diagram like this. On this side are the atomic orbitals. On the other side is the atomic orbitals. In the middle is what you calculated for the energy sequence of those so-called molecular orbitals. And if you think about those are for the second row, so you start with second row, you start with lithium and beryllium, then you have boron, carbon, nitrogen, oxygen, fluorine, and neon. We do not have those first two in here in this picture, but they will be similar. What you see is you see the what you did is do the linear combination. Your educated guess for these two is starting from 2s plus 2s, plus or minus 2s, depending on how much you use. For the homonucleus diatomic molecular, you pretty much the best way is just try to use 50% and 50%. You put them in the same weight. So this one is the result of adding these two together. That one is subtracting the S with S together. And then you do the similar for the other, then for those molecules. But then you notice there's a little difference, so I will also see there's some of those differences. So why there's like this pi 2p is lower in energy than this here, that's kind of out of sequence, is because when you do the calculations, if you have time, you don't count only like take the S, 2s with 2s, you can take more and more. You can take 2s from this side. You can think about like 90% of 2s plus 10% of the 2p, and then maybe plus 80% of the 2p and 2% of the 3s and so on. So you will try to have those mix. So usually those when you try to use those mix, not only use S, and that is more like less important than depend on those molecules. Okay, so the result is for those small atoms, so the mix is a little more dramatic than compared with those large atoms. So therefore, you will see those their sequence, their orders. As usual, we predicted. What we predicted is those S type of overlap. I mean the sigma type of overlap is more stable or have a larger overlap region than those pad type of overlap. Right. So now once you have those order of atomic orbitals, and what you can do is you just use those meter diagrams, those squares, and populate the electron in it. It's very similar to what you did for Chapter-7. Once you have those electrons in the square, then you will see where the electrons are. If the electron in those square that don't have the star, sigma 2s, sigma 2p, or pair 2p that don't have the star on it, so those orbitals, their energy like is lower than those atomic orbitals. You call those molecular orbital the bonding molecular orbital. Right. So then you just populate or just put electron in those middle squares according to what we did in Chapter-7. If you have 2 electrons, you will put it here. If you have 3, you put 2 here, 1 here. If you have 4, you put 2 here, put 2 there, and so on. So then once you have those information, you can calculate the so-called bond order. The bond order will tell you how many bonds between 2 atoms. If the bond order is 1, that means you have a single bond. What is the more? This theory will tell you you can also have those half bond. Now in the other 2 theories, you don't have that. So you don't have to really have a bond or a triple bond, double bond. As long as you have some bond and you have those stabilities. So you just take those number of electrons in the bonding squares that don't have the star, and subtracting by those electrons in those stars and divide by 2. Right. So here are a few examples. So let's see this. This is B2, and you will see there's B2. Because all those stars, the lowest one is 2s. That means we don't think about those 1s. So all those you are going to use the valence bonding, valence electron. Okay, so each boron has 3, right? So group of 3A. So each boron has 3 valence, and you have B2, so therefore you have 6. So you have this kind of diagram, and you put 2 here, put 2 here. Then you have 2 electrons, you have 2 squares. Then you spread them out. Right. So then you calculate the so-called bond order. How many we have like 2 bonding electrons here, and then plus 2 more bonding electrons here. So we have 4 bonding electrons. Then we have 2 non-bonding electrons. 4 minus 2 divided by 2 is 1. So bond order is 1. Got that? So I think you have those kind of questions on the quiz. And you'll be able to use those diagrams and do a calculation. And all those calculations here is new to you. And now let's do like one more practice. If I want you to calculate N2 like 1, let's say 1 minus. N2 1 minus. And so then you know N2 is use those type of orbital diagram. Okay? So just counting out how many total electrons N2 1 minus has. Right, so 2 times 5 plus 1. We have 11 valence electrons. Am I right? So now, on this picture, you already have this 1, 2, 3, 4, 5 pairs. That means you have 10 electrons. Right? And according to our calculation for this ion, we should have 11. So we have 1 more electron on top of this. Just go by 1 by 1. Now all those are occupied. So the next door available will be this type of orbitals, a molecular orbital called the pair 2p star, which means anti-bonding. But you have no choice. You have 1 more electron. So what you do, you will put it here. Get it? Okay. Now you calculate the bond order for this N2 1 minus, which equals how many bonding electrons? How many bonding electrons we have?
10.
we have 10 bonding electron. And how many like anti-bonding electrons? Altogether. Very good. So we have, let's say we have one pair here bonding, that in the sigma 2s, no stars, so that's bonding. Okay. One pair here bonding, two pair here bonding, and three pair bonding, right? And one more pair here bonding, and well, actually we miscount, right? And how many bonding pairs we have? 8. I thought we have 10 like minus 4. Okay, so actually we don't have 8 bonding electrons. We don't have 10 bonding electrons. We have 8. All right. So now let's count how many anti-bonding electrons. How many anti-bonding electrons here? 2. And how many? What else we have? This is bonding. Then plus 1 here, right? So altogether, how many anti-bonding electrons? 3. Okay. So there we get 5 divided by what? 5 divided by 2. And so for this one, you have the bonding order 2.5. 2.5. Now, what is the bond order for N2? What is the bond order for N2? So the bond order here, bond order for N2 is what? 3. So now once we have that, you can think about which one is more stable. Which one is more stable? The N2, the larger the bond order, the more stable. Remember, the bond order means how many bonds you have. The more bond you have, the more stable your molecular ion is. Get that? So compare N2. N2 is more stable. More stable than N2 1 minus. What's the reason? What's the reason? What we use is bond order, right? Bond order for N2 is how much? 3. Bond order for N2 1 minus, right? Bond order for N2 use bond order, right? Use bond order. Get it? Okay, so bond order, let's see, for N2. For N2 is what? Is 3. Bond order for N2 1 minus is 2.5. It's very straightforward. The larger the bond order, that means there's more chemical bond. The more chemical bond, that means it's more stable. For the same term. You don't compare like N2 with C2. Okay. Just compare N2 with N2 first. Right. I mean, for this one, you can compare N2 with C2. C2 is 2 and N2 is 3. But if you have some other molecules, like what we said before, C2 and H2, then between C2 and C2 you also have a triple bond. Then triple bond, that means a bond order 3, then 3 and 3 you cannot compare. Okay? So in general, just compare with the same. Alright, I think this is about what we said here about the molecular bonding theories. So then in summarize, there are 3 bonding theory. Let's see, I think about put one more CRE on this quarter, probably not a good idea. Let's see if you can summarize. Loose bonding theory is about covalent chemical bond is the sharing of electrons and represented by dots. So I get started for the loose bonding theory. And now you think about in this valence bonding theory, what is the definition of a covalent bond? In the valence bonding theory, we emphasize is doing what? Those atoms doing what will get low energy and produce a chemical bond. They use S or P or SP2 or SP3, once you know what they use, what do they do? Overlap. Overlap. So overlap is an example is that. So in the valence bonding theory is overlap of most commonly is the half field those atomic orbitals, but those atomic orbitals may be hybridized, maybe the standard. One example, we still use ozone O3. Lewis structure, Lewis theory will tell you, I missed one here, we have O there. And you can either single bond here, double bond here, or double bond here, single bond here. Or you can think about use valence bonding theory. Valence bonding theory will tell you it's hybridized like those. So I will leave it to you to think about what is purple one standing for. The purple orbital here is standing for SP or SP2, SP what? You don't need to know. So this purple one is SP what? SP2. Very good. So then that is the one thing that tell you like this. But the problem is you from the prediction of this valence bonding theory, because you can overlap like that, and that tell you you can have one single, one double. But experimentally, there's no single and double. All the bonds are single. Hold on. Now let me ask you, what do you predict? How you produce a chemical bond in the molecular orbital bonding theory? This is what we just did in that bond order, think about bond order, right? So what do we produce? How we produce a chemical bond when we think about the molecular orbital bonding theory? Field orbital, and then if you see like there's more electron in the bonding orbitals than those electrons in the anti-bonding orbitals, then your energy for the result of the molecular is lower. That means if you have non-zero bonding order. So the chemical bond is the electron in the molecular orbital that result the lower energy than the atoms separate apart. So what is important is the molecular orbital bonding theory is emphasize those electrons is spread out all over the molecular, and so all those theories sometimes is similar, but sometimes it's different. So according to Lewis bonding theory, you don't have a double bond, single bond between any atoms. You will have one and plus a half bond between both pair of oxygen atoms, and that can be explained by using molecular orbital bonding theory. So you have this is one of the molecular orbital theory, molecular orbital diagram. There's another one. So adding together, you will get those kind of result as what you get from the Lewis bonding theory. Right. So this is about the Chapter-10. You keep the central and flip it over, and then you will see that used for Chapter-11. Okay, so I'll probably will lecture about 30 minutes or so on Chapter-11. And then I will give you about 30 minutes, or we'll talk about the lab, use about 30 minutes. Okay, so Chapter-11 is about, it looks like it's different. It's about the liquid, solid, and intermolecular forces. It's about the state of the materials. And so some of the common characteristics of those material in different states is summarized in this table, and it's very important. Okay? Let me change this project a little bit. So this chapter is the last chapter, and we will be able to finish this chapter like Thursday, and then Tuesday we'll have the final. So this table summarizes some of the common characteristics of the three states. And we think about what are the shape for the material in the different state, what are their volume, what are their density, are they compressible, can they flow, and then what is the strength of what we're going to study in this chapter, the so-called intermolecular forces. So we have a solid, liquid, and gas. And the shape for the solid is fixed. For the liquid, it's not fixed because you can have a different shape depending on the container. And obviously, the shape for the gas is also not fixed, it's indefinite. And the volume for the solid is fixed, for the liquid is fixed. Usually, you will not change the volume of the liquid too much. But the volume for the gas is indefinite. Density for solid is high, density for liquid is high, density for the gas is very low. Compressible or not, both solid and liquid cannot compress too much, but you can compress the gas a lot. Whether flow or not, you cannot, the solid cannot flow, obviously the liquid and gas can flow. Intermolecular forces, for solid is very strong, for the liquid intermediate, and for the gas very weak. So you probably will know those kind of your common sense, but it's very important to know that. So then, not only those characteristics, and also have one characteristic not in the table is the degree of freedom. So the so-called degree of freedom, we have a different type of a degree of freedom, and for each type you will have different numbers. So the common type of a degree of freedom is these three types: translational, rotational, vibrational. Translational, you usually think about the three of those translational, because translational, you can go that x, y, z is three coordinate. Rotational depends on the complexity of the molecule. So as your molecule become more and more complicated, you have more and more rotational freedom. You can rotate it that way, rotate in that axis, in that axis. Similar for the vibration, because you have more and more chemical bond, you can have more and more vibration, then you can imagine that. So then you can think about those different same material in different states have a different degree of freedom, and you can also think about in another way. So what material in what state depend on how much freedom they have, and also depend on like the other quantity, like depend on the how much how strong the force in between the molecules. So let's see, just simply think about the molecule have a different freedom in different states. And the ideal gas, obviously we think about ideal gas or real gas. For the ideal gas, you will think about they have completely freedom. There's no limitation because ideal gas, that means no attractions, no repulsions. And then in the other contrast, those material in solid has the least freedom, because that's in solid all those molecular or atom or ion just locked out. Then those molecular, even though I see the molecule, but you don't think about the always a molecule, sometimes maybe atoms, have limited freedom. They pretty much still have everything like rotational, translational, vibrational, but all those are limited because the nearby molecules. Right. So the state of the material depend on couple of things, depend on the amount of kinetic energy, which is depend on the degree of freedom, and it depends on the strength of the intermolecular forces. And this is two of those major variables. So these two are competing with each other. So if you have more of that means you have more freedom, then your material will try to be in those gas state. And if that dominates, then your material will be in the solid or in the liquid state. So you talk about the kinetic energy, it pretty much, you can think about increasing the kinetic energy or increasing the motion energy of the particles. And then in the given material, you have different molecules and they will have different kinetic energy. But you can think about the average for a given number of material. So then the average kinetic energy is directly proportional to the absolute temperature in kelvins, and that is given by that. Just that give us some idea about the kinetic energy. That is about the average kinetic energy that is proportional to the T in kelvins. And those attractive force is kind of the main focus of this chapter. So we will study those what are their type and compare their strengths and so on. So again, this attractive force competing with the degree of freedom or the kinetic energy, and if you have more kinetic energy so large compared with the attractive force, your material pretty much will exist as a gas. And in particular, if your gas is the ideal gas, you have all the freedoms. And so therefore, we don't have too much limitation on the rotation or on the translation, and the gas particle can go to every part of the container, every corner, every line, or every edge, every side. And also that tells you the gas can flow. And there's a lot of empty space between gas, therefore gas is compressible, and that's one example. On the other side, you have the solids. See the solids, compare the freedom with the force. So the force overtaking, so you don't have too much freedom. So therefore those particles in the solid pretty much stuck together. So that in the middle you have those liquids. So you can see they have all the freedom, but all the freedom is limited. Right? So you keep the two factors in mind. One is like the freedom, the other is the attractive force. So they competing with each other. So you change their relative strength, and you can change the state, you can change the phase. And you should be able to know those common terminologies. Right? So when the attractive force becomes relatively weaker compared with those kinetic energy, then your material will change gradually from solid to liquid and to gas, vice versa. You probably want to know those names. And so here we have four step of phase change. You start with solid and go to liquid, so that we call that melting. And then continue adding heat as what we did in chapter 6. You are adding more and more kinetic energy because the average kinetic energy is proportional to the temperature. You're adding heat, the temperature increases. So your liquid becomes warmer and warmer, and finally you become that boiling point, and then before the boiling point, even though some of those become vapor, but in the boiling point you become vapor. So this becomes vapor. This is called vaporization process. Right. So reversely, and you can cool the gas, or you can apply pressure to the gas so that the gas can condense into the liquid, so we call that condensation. And if you continue, if you continue with lower the temperature, or apply pressure for most of the material, some of the material, if you apply pressure and you don't change temperature, you can never change them from liquid into solid. But anyhow, if you see the process change, if the material change from liquid into solid, you call that freezing. And you can also add in one more step. You can skip the liquid. You can go from solid directly to the gas. And we call that sublimation. And vice versa. You can go from gas directly to solid. Deposition. Example is frost. In the winter time or in the autumn time, in the morning you'll see the frost, and even though you did not see the rain or snow, so where does the frost come from? Comes from moisture in the air that directly change from gas and into the solid. The sublimation, you also know that so the disappearance of ice cube in your freezer. You have those ice maker, okay? And you'll see sometimes in winter you make those ice cubes is pretty big, but if you don't use those ice cubes gradually, they become smaller. Even though you did not see the melt. Right? So as I said, the main topic of this chapter is about intermolecular forces. So I want you to know what is the type, or I'm going to start with what are the types, and what are the relative strengths, and then how do we know what molecular or what matter has stronger intermolecular forces, what method we use to tell that. And so before we start those details, I want you to know the difference between the intermolecular forces and the chemical bond. Okay? So intermolecular forces is not a chemical bond. Okay? So even though sometimes we will compare the intermolecular forces, okay, with the chemical bond, you see this word here have the inter, which means you keep in mind you will have all those molecules still exist. Okay? And just think about what are the attraction between those molecules. Sometimes you might have those mixture, maybe between an ion and a molecule, and that is still not a chemical bond. Okay? So those chemical bond and intermolecular forces is different, but sometimes they have something in common. What is common is their strengths is all followed by the Coulomb's law. So all those attraction, the chemical bond or the intermolecular forces is not a chemical bond, is determined by the Coulomb formula. Okay? Very similar to what we studied in chapter 9. It's about the lattice energy. Okay? So you have the Q1 and Q2 on the top, you have the R at the bottom. Okay? Similar as what we studied, similar as lattice energy. So therefore, you will see the larger the charge, what it means the Q1 and Q2, okay, is larger, and then the attraction is larger. Obviously, if the distance gets larger, then the attraction is weaker. And this is the two reasons why the chemical bond is stronger than the intermolecular forces. Okay, now see this picture. So between this bar, and we're assuming that is our oxygenator, and this is our hydrogenator, okay? And that is the chemical bond between oxygen and H. And then compare the attraction between this oxygen and that, this hydrogen, that oxygen, and these two is in different molecular. So this H is in one molecular, this O is in the other different molecular. Right? So this dotted line representing the intermolecular force, this solid line here or the solid bond here represent the chemical bond. Now we will see the chemical bond is stronger than this dotted line because of these two reasons. One reason is Q1, Q2 for the chemical bond is larger. So even though you don't have the Q1 on the oxygen, you don't have the Q2 that's not on the oxygen, but when you do the calculation, you can think about in the middle there are some of those negative electrons. Then negative electron attracting to that, negative electron attracting to that, and that is a lot of charge. Compare with this, this because you don't have too many net charge on the H, you don't have too many net charge on the O, nothing in between. So therefore, it's much weaker compared with the chemical bond. Right. So then, how do we know what kind of material have a larger or stronger those intermolecular attraction? Okay. We can use different some of those macroscopic quantities. For example, the normal boiling point is one of those macroscopic physical quantities can measure. Melting point is another one. Vapor pressure, like what we did last week in the lab, another one. Viscosity and surface tension. So vapor pressure with viscosity and surface tension. Right, so those all those are different microscopic physical quantities you can use. Okay. For this few we mentioned here, boiling point or melting point, viscosity, which means how easily they flow, surface tension, which means you can see the surface tension, for example, you see some of those floating on surface of some of the liquid. So all those except the vapor pressure is directly proportional to the strength of intermolecular forces. Maybe not that good directly proportional, because in terms of some small scale directly proportional, meaningless proportional, but at least tell you if the intermolecular forces increases, your boiling point will increases to a higher boiling point. And then similarly, your viscosity will be higher, your surface tension will be higher. The vapor pressure will be opposite. Vapor pressure, if your vapor pressure is larger, which means your intermolecular forces is weaker. So as what we studied, what we do in the lab last week, we measure two liquids, one is methanol, the other one is ethanol. So now we know ethanol has larger intermolecular forces, and later on you will see why that is larger. And therefore, when you measure the vapor pressure, you will see the vapor pressure of ethanol is lower than the vapor pressure of methanol. Right. So then, what you want to compare those different forces in this chapter is pretty much that 5 type. But for the phi type, we call them intermolecular forces. And this slide tells you we have three of them. So we have that dispersion force, relatively is the weakest one. And then we have the dipole force, relatively that is stronger. Then we have even stronger is the hardening bonding. I emphasize this relatively speaking is because the weaker one can become dominant if you have more weaker one. So I think the better comparison is to compare for the same molecule, for the same material. For the same material, see what is the strongest force for that particular material. For different material, you first want to compare per unit of mass. For example, per gram. Per gram, per kilogram. You don't use per mole, per molecular. Because mole have different mole mass. And then mass, what we see in this chapter, play a very important role. So even though something what we talk about here, this dispersion force is relatively weaker, but if you have more, a lot of those gram of the material can have this dispersion force, that can make it very strong. Right? So you know the type of those intermolecular forces, then you know their relative strength. Then let's see examine one by one. Right? So what is the origin of the dispersion force? What is the origin or what is the definition of the dipole force, and so on? Dispersion force is a force that is relatively weak in terms of the program because it's very, very temporary. Okay? But it's for every type of material. No matter material is polar, non-polar, has H bonding to O, and so on. So you always possibly have this dispersion force because the dispersion force comes from the so-called temporary dipole. It's kind of a temporary distortion of the electron distribution. So you study those different bonding theory, you know those where the electron most of the time they are. Okay? You also study Chapter-7, like what most of the time the electron in the atom where they are. But you can temporarily have the distortion. I mean, you can have a temporary, like those stream of distribution of the electrons. Okay? For example, if you consider those noble gas atoms, so we usually think about those noble gas atoms. Those atoms is a spherically sphere, which means the electron is evenly distributed all over the nucleus. Okay? But the electron is not really fixed in the space, in the location. And depending on the time, so at one time, if you take a picture, so these two electrons in helium might be in these two locations, in another time like that. So once something like those happens, that two electrons both get on one side. So even though that's the lifetime for those kind of structure is very, very brief, but it can exist. When that exists, so you have the relatively negative charge, more negative charge on one side, and more positive charge on one side. Those kind of like distortion, because usually they are symmetrical. Okay? So when that happens, if a nearby atom exists, and so you have a positive side on this side, so that will going to attract the electrons on the other atom. So then one by one, and you have those temporary dipole, induced dipole, and so on. So then once you have those electron distribution not even, then you will have those attractions. So this is the origin of this dispersion force. It's very general for every type of material. So keep that in mind. No matter your material is polar, non-polar, 1 bond or 1,000 bond. So you always have that. Obviously, if your material have 1,000 bond, even though your material is non-polar, because that 1,000 bond have a lot of those electrons in it, and you have a very, very large dispersion force for the whole material. Right? And so then for one particular material, we want to compare, those strengths between like one material with another material, kind of. So then that's the dispersion force strengths depend on two variables, depend on two factors. One is the mass, okay? The other one is the shape. This is very similar to memorize. So you think about the larger the mass, okay? Or the larger number of atoms, electrons you have in the molecular, and you have a larger dispersion force, because you have more possibility for those distortions. And then the shape is also very important. Okay? Because we know that force is proportional to Q1 times Q2 divided by R. The shape will influence your R. So if you have a shape and you have more like those pair of points that has a small r, and so then you will have a larger those dispersion force. Okay? Now let's compare these two pair of molecules, and they pretty much have the similar shape. Okay? They have a similar shape because this is oval, this is oval, this is oval, this is oval. So by the picture that show you this pair of molecular is a larger molecular. That pair of molecular is a smaller molecular. Okay? So a smaller molecular, which means you have a smaller number of electrons in it, a small number of proton, neutron in it, that means you have a smaller mass. Now this larger molecular, you have more electron in it, more atom in it, so therefore you have more mass and more gram. Okay? Then you will see which pair have a larger dispersion force. The bottom one, because they have more of those attractions.
Touch more?
They can, well, they touch more, depend on the, yeah, you can think about that, depend on the, you can see that cutting line here, right? So this only have these few pairs, and there you have more pairs. Okay? Yeah. So, yeah, also touching more, touching less, yeah, that's good. So you have more electrons, obviously you have more touchings. And then the touching also depends on the shape. Okay? Now for this, see the middle one, they have small r. So if you start one pair, then in the middle, this pair here, this pair here, right? So this pair have very, very small r. If you choose one pair at the side, this will have much, much larger r. Obviously you can have all those cross points, but just give you some idea, right? Okay. So very good. So the bottom one has a lot of dispersion force. You can think about that because we have more of those pairs that come from more electrons. And so now, as we said, how do you know that is true? You can think about that is true. You can think about that is true by use that a few of those macroscopic quantities. We talk about the boiling point, melting point, vapor pressures. So here we have those boiling points. and we compare this few those noble gas. And obviously, by comparing them, we eliminate one of the two variables. Well, we know that this dispersion force depend on the shape, depend on the mass. Okay? Now all those noble gases added, they all have the same shape. Now this boiling point, in general, they will depend on all type of force between the atoms or between the molecules. Now here you're going to compare those force between xenon and xenon, between pre-veton and pre-veton. You don't do the mix, right? So depending on all the force, and so even though here it's kind of early because we did not see the other forces yet, we only know the dispersion force. Right? If the molecule or the atom has other force, you're going to compare one by one. Right? Now for this normal gas is similar. There is no other force at all. The only force between like xenon and xenon, or between pre-veton and pre-veton, is the dispersion force. No other force at all. Okay? So therefore, we can simply use this pattern of the boiling point as an index for the strength of the dispersion force. Otherwise, you cannot simply use that. You can only say the pattern of the boiling point only give you a pattern for the intermolecular forces. And that will be the overall for all the forces added together. Right? Right? So we don't have any other forces. The pattern tells you the boiling point, you go from top to bottom. So as the molecule or as the atom getting larger and larger, the boiling point is getting higher and higher. So what we said, boiling point, melting point. So even though the melting point sometimes maybe have those, for small one have those little variation because those are the crystals. Crystal structure depend on how close they are. So usually the boiling point is the better index, and with viscosity, surface tension. So those are like directly proportional to the intermolecular force. Okay. So higher boiling point, stronger forces. Only forces for those kind of material is dispersion. So that's perfect example that I agree with what we said. Alright, so I think I will stop here, and we will continue on this chapter 11 and finish this chapter 11 very quickly when we come back Thursday, because that's the only day before the final. Okay? Now talk about the lab. And okay. So what you do in the lab, you have that table. You can turn in the lab like on the 18th day by the final on December the 15th. Okay? So then we get the lab, and so now we talk about the lab. So we basically finish all those concepts of this lab. What you do is try to finish the table, right? So I think most of the molecule is trivial. For example, H2O, you just you go by column. First you draw the root structure, identify what is the center. Some of those simple molecular like HCl, for most of those is not really applicable. You don't have that electron geometry like for HCl, but you can still get loose structure, right? So we talk about pretty much that 5 basic geometry. So we start with like 3 atoms, 1 center, 2 terminal. If you see the next one, you have some of those molecules very simple, HCl, HI. You can still draw the loose structure. HCl, you have 1 H, 1 Cl. You see how many total electrons. But those not really what we talk about. What are the electron geometries? What are the molecular geometries? You can just see Na. We did not study those kind of concepts. Got that? For HCl. HCl, you can draw the structure. You see H and Cl. All together has 8 electrons, right? So you put 2 here, and then you put like 3 more here. So that's the structure. And then we usually don't talk about what the electron geometry of this, what the molecular geometry of that. So that's very simple, just 1 line, 1 bond, and linear. But you can identify those polar and non-polar. So this hybridization is not applicable. Molecular geometry for HCl is Na. Electron geometry Na. Hybridization Na. But you can identify HCl is non-polar or polar. That's very similar if the molecule has only 1 chemical bond, right? And then your polarity for the molecule is the same as the chemical bond. So for HCl, there's only 1 chemical bond. And then we know this bond is polar. I simply use the electronegativity for H is 2.1, for Cl is 3.0, so the difference is 0.9. So you know this bond is polar. There's only 1 bond, so no way it cut off. So therefore your whole molecule is polar. For others, you have to use what we talk about here. If you have more than 1 bond, 2 bond, you will just draw the loose structure, right? For water is H2O, and then you know O is the center, and then H, right? And then you also have 8 electrons for this H2O. So you finish draw the loose structure like that. Now you have a center atom. You have this oxygen center atom. And then you can finish those counting the electron groupers and see what is the electron geometry. Is this a tetrahedron, right? Is it linear? And then you can use whether you have long pair and find out the molecular geometries. So once you know the molecular geometries, you'll see that belongs to that 5, or that 5 is modified. And you can see here, all these 5 here is basic. Okay? And this 5 is basic plus 1 modified. Very easy to memorize, because this 5 we talk about a lot. This is the electron geometry. It's the 5 basic geometry. And this 5 electron geometry, maybe also your molecular geometry, if your central atom don't have that long pairs. Now for, you just apply what we did for each 1 center, if you have more than 1 center. And so then in this lab, you don't have to worry about you have so many centers. So if you have more than 1 center, you have 2 centers, 3 centers, and usually, as I talked about before, the simplest scenario is if you have 5 center atom, and only 1 center is polar. All other 4 centers is non-polar. Then that's kind of like in the transition, almost like you have 1 center that can not overtaking all those 4 non-polars. But if you have more than 4, you have 5. So even though you have 1 center in the polar, then your molecular become non-polar. Those are the typical supermoleculars. All those molecular in those like vegetable oils. So those like those so-called fatty acids. So they will have like one part that is polar, that is polar head or polar end. Then this all the other part is non-polar. So you can use those theory depending on how decide on those small molecules or large molecules. Keep in mind, and you have to use them one by one. So then let's go back one by one. Let's identify what is the center. So then you will be able to write the Lewis structure, right? So the first one, obviously, you want to get the Lewis structure. You know the center is what? Center is O. The second one, the center is B. Very good. And then this one is ion. Don't forget, negative ion. When you count the electron, you want adding one, right? So then this one, the center is N, right? And then this one, the center is S. So when the molecule becomes tedious, you possibly have more than one center, but you can decide like which one is better. You can use the former chart. So that is P will be the center, and those is not really applicable. HCl is only two atoms. ICl not applicable. Br2 not applicable. CH4, the carbon center. Get that? So CH4 carbon center, and then what about this? This is the H. Well, you can think about that. O is the center, but not that. Well, you can think about that. O is the center, yeah. But this is the so-called oxalic acid. Okay? Oxalic acid. You think about actually what is really center is CCl, but actually, yeah, just keep that, make it simple, just use that O as the center. Okay? So O is the center, so therefore H is bonding to O, Cl is also bonding to O. If you have some other similar, those kind of structures, okay? And if you have O2 like Cls, and then you are make that really make the Cl become the center, so then you have that Cl center. That O is also center, but the more than one center, you put the interior. I probably will have that. For this one, just write that H bonding to O. Get it? And so let me see there. So here you will have H bonding to O and bonding to Cl. Right? If you have another O, and you have something like this, okay? And that will make you have like two centers. Right. So the next one again will be the P is the center. This one will have two center. Your two center will be N is the center, and O is the center. And because of that, when you think about the electron geometries, if you have more than one center, you have to tell me both center. You will see the electron geometry for N is the tetrahedron, right? Electron geometry for the O is also tetrahedron. Continue. O2 is not applicable, just O with double bond, not O. Each O has two lone pairs. So that is our formic acid. So the second one you have a carbon, and let me forget about the double bond, single bond. I will just tell you what is the center. Tell C and O like that, and like that. And then you have another O. So then you will finish all the other. I think I already read those.
So what were the two centers on that one?
The two center will be the carbon and O. So you have one carbon and one O. So you have this, and another O, another H. Then you have to finish. So this is pretty much the main art of the atom, but you have to finish the the overhead for the atom, if they need the overhead, but if you don't have electron, you might use double bond, triple bond. Very good. So then the next one is the C2HCZ. What is the best structure for the next one is you have two carbons. When you have those multiple carbons, those are usually those organic compounds. So what you do is first use a single bond for between the carbons. Right? So then you have an H. So you can put on any of those places. Okay? And then you have a 3Cl, so therefore you can put that. So that is the better. Okay? And you don't think about put all the Cl on one carbon. Okay? So distributing them like that. So similar for that C2H2, you probably already saw that before. For that C2H2, you will have C and C and that, then H and H. So you first just use a dash like that. Now again you have complete overhead for all the atoms. Alright. CO2, SO2, you know, S is the center, very simple. CO2 carbon is the center. Now the next one is also very, very tedious problem. C2H2O, 1O, right? So I think the best structure, the most stable structure, is like this. You have one carbon. I said you have more than one carbon first, make them out like this. Then you have an O, and cell H like this. So this will be your best layout first. And another structure layout is carbon, and O. So something like this. Try these two first, and then for this one, you will have two different ways to make them overhead. And one is better than the other one. I think all the others is very straightforward. N, O2, N center. That is the problem because that one will have an odd number electron. So no matter what you do, one atom will have an odd number. N is 4, N in the center. SCN1 negative. SCN1 negative, just as what is written S, C, and N like that. And that's what the best structure. Obviously, that is negative 1, so just put negative 1. You can play around, you can see that. Maybe try something else. Try like S and N, then one C. You just scramble those atoms, then you can calculate the formal charge. I think the best one will be that. The best layout for the atom for the SCN1 negative ion of that. All right, I think that's about it. If you have the molecular model set, then you can play with that. Molecular model set, and I think usually we have somewhere here. They're pretty much just those, you have those balls and a stick. And you can just, if you want to produce a tetrahedra, you just. Okay, any questions? Alright, so then we'll see you like a Thursday. Thursday we'll finish Chapter-11. By the way, you are turning on everything like on the, if you did not turn in yet, on the final, which is December the 15th, okay, next week today. Thank you.
So I got all these done except for the organization.
Right.
For today, and flash. So let's say for right? We're looking at this here. There's count 1, 2, 3, 4.
Yeah, okay. So,
S, P, 3. Similar flag for this here.
move first.
He didn't put the boxes. Because there's 2 ways.
Yeah.
Yeah, well,
This one's 5.
Yeah. Mhm.
See how that's like.
Yeah.
well, it's linear, it's just SP.
Also,
This would just be a linear. There's no non-bonding.
but everyone was crazy groups.
It shouldn't be, if it's linear, it should just be SP.
No, that is really too crazy. Basically, all of this is, yes.
You can ask him.
Oh, did you receive any like email from the department yet? I think Professor Wall will tell you, right? Email. Yeah. What did she say on email? Did you tell you?
Did you make the graph for the other one? Oh, because I answered the question.
Same thing.
If you didn't, I can make it.
I think it should.
Yeah, you just
I
take
forgot
it very,
about it.
you
I was
just
so
tell her,
into
email
this
her.
thing.
Okay.
And the rest of
I answered the 2 questions.
I'm gonna do both of
I
them
think that
at home
means-
and then just
I
try
don't
to
know,
get it
that
for
kind of
you.
using, is that all the
And
time?
see
or
if it
she's
matches
out?
with, it's not that hard to make.
Because-
No, yeah, I mean, I was gonna do it, but then you said you did it, so I was like,
She
oh,
was
that
saying
was a waste of
the
time.
I'm so sorry, guys.
No, it's okay.
Okay.
This,
I'll get it for you
Let them
too.
know, like, let them like, you take the test and, you finish, email me, and, what do you do? How you get the test back? Send them back with, probably the work and pick them up or?
Yeah, something like that.
Okay, don't worry, so I will just.
so this page has a crazy ones on it. So when I do it for both of these two,
Right, just identify those.
this is like C,
Mhm.
this is O,
Mhm.
so it's P1, 2, 3,
Mhm.
SP2.
Very good,
O, B1, 2, 3, 4, SP3.
very sorry, very good.
Okay. This one, no. I'm trying to think of. Okay, I think I'm good.
Okay.
Oops, sorry.
Sorry. So for like this, for this O2,
Mhm.
like it'll also be SP, right? Because.
No, those two, if they only have two, we just say they are not applicable.
Oh, we don't say, we don't call linear,
We,
it's just 2?
yeah, we just say they are, they don't have those hybridations.
Oh, for here?
Yeah.
You don't say that?
Yeah, just.
You still say linear though, right?
You can see that linear.
Okay, but you just say NA if there's only 2?
Right.
Or so like for N2, it'll be the same thing?
Mm-hmm.
Oh, I just thought if it
I
was
was
linear, it
curious
was
because
always
I just overheard you saying tetrahedral for this one. It's not square.
No, we don't have that.
Electron geometry is
Yeah,
also
electron
square.
geometry, molecular geometry, we don't have that. But we really don't have assignment, so what do you do, just negate,
And they,
and not applicable.
for electron geometry?
Yeah, yeah,
Are you sure?
yeah, that's what I think. Okay.
Okay.
Well, what if we put one here, are you gonna mark it wrong?
High relation, I was looking at it, says SP2 for this one.
No, you don't, I think we.
I just asked you if I could call it linear and you told me yes.
So is it linear electron geometry or no?
Oh, this would be electric. No,
Yeah,
yeah,
like
electron geometry.
molecular geometry, you can see.
I can say linear, but I can't say linear for that?
Because look, there's really,
I don't know, yeah,
Okay, so it was a question mark.
Well, if you don't know, who's gonna know? You're supposed to know everything, come on.
Anyway, I have a question for you.
I don't like putting up with stuff that's too hard for us to do.
Oh, I'll confuse right here.
That's just a minute.